Right, line A4, learning task 8D video that we're going to go and do, where we are now going to deal with our resonant circuit that we have inside of here. Now we've covered parallel RL, we've covered parallel RC, and now what we're going to move on to is a RLC circuit that has got resonance that's going to be happening inside of it. And they've given us a fairly incomplete looking circuit, the whole point being that we should be able to go and solve for any of the missing values that are going to be part of this. All that they have told us is that this circuit is going to go and be resonant at this point. And if I've got a resonant circuit, that means that I understand that XL has to be equal to my XC. So over here, even though I don't have any value whatsoever for the capacitor, I can go and figure that XC of this capacitor out by figuring out my XL of my inductor over here. And I can figure out that XL of my inductor by using the millihenries and the frequency together. And once I've done that, that'll allow me to then create an XL, which will allow me to go and create an equivalent to XC. And then from that XC, I'll be able to go and work my way backwards down into the actual capacitance itself. The other thing that I'm going to be able to do is establish my total amount of power that I'm going to use by the circuit itself, continuous power that I'm going to go and utilize. And we know that if XL is going to be equal to XC, my bars are going to have cancel each other out, and really, I'm only going to go and have power dissipated out of this circuit. There will be, once again, an inrush. When the circuit is first energized, there has to be extra current that's just going to flow for a split second just to fill the plates, based upon the size of the capacitor. But after that, those electrons that fill the plates are just going to be passing back and forth from inductor to capacitor, and they're just having a good time over here at this end of the circuit, while the rest of our circuit is doing true, useful work creating heat through this resistance that we have over here. Okay, let's start with some values. They ask us for the capacitance, they want to know the inductance, they want to know the current, they want to know the line current, they want to know my impedance, they want to know my apparent power, so the VA of my circuit, and they want to know my power factor and my phase angle. Let's start with the power factor and the phase angle, because we know that if we are resonant, all power has to be 100% used by my resistor over here, which means that my power factor should be 100%, and my phase angle should be 0 degrees. In other words, everything will be along that x-axis. We'll come back to this later on and just do the proofs off of it, but we might as well chuck in those numbers right now because we know. All right, let's start with our XL. XL is equal to 2 pi FL. I do have my frequency, therefore we should be able to calculate this. So we are going to go and take 2 times pi times 60 multiplied by my L value, which is 0.042 because it's millihenries. Remember that milli is thousandths. Don't stick in 0.42, you end up with an incorrect number. When I do that, I come out to a XL that is going to go and be equal to 15.833 ohms. Okay, we'll place those inside here right now. 15.833 ohms XL. And because it's my XL and we're at resonance, I know that it's going to be the same for my XC. 15.833 ohms XC over here. Lovely. That's an L over there. Sometimes my L's and C's are similar. We'll make that more L-ish looking. All right, so we've got XL and XC that are now placed into my circuit. From this XC, I can work my way backwards down to go and figure out what my C value is. Now, if you go into the binder, they go and take the two formulas and they place the two formulas together, and then they do this fancy little bit of math. There's nothing crazy about it, but it's just a little bit more extra than what we actually need for this. If we want to go and find our XC, we know that XC is equal to 1 over top of 2 pi FC. So I can just go and multiply C to the top and XC down to the bottom. XC to the bottom, we'll move C to the top. And when I do that, I've now got a formula that I can go and punch in to find my value of capacitance. So I know that this value of XC that I've got, multiplied by 60, multiplied by pi, multiplied by 2, and then all reinverted is going to go and give me my C value. Luckily for me, it's still stored in my calculator. So I'm going to go and, without clearing this out, because that's right now a super accurate number we have, multiply that times 60, multiply that times 2, multiply that times pi, and then I hit answer. It's going to spit out this big number, and then we have to go and reinvert that number because right now we have not gone and done that yet. So we'll do that, and we come out to a value that's going to look like this, 0.000167528. This is milli. This is my micro range. So I see that this thing would have to be 167 microfarads. Note that in your binder, they just say farads over there. Go and change that, put in the little mute over there, 167 microfarads. Lovely. Okay, so now that we have got my capacitance, my XL, my XC, what we can do now is we can go and apply our power over top of stuff. I see it's a 240 volt circuit, so I'm just going to do E squared over R, and I'm going to go and power my way through this entire circuit over here. Start with our watts, E squared, 240 squared, divided by 20, my R value, equals a value of 2,880 watts. 2880 watts, put that in there. We'll then move on to this one over here. Our inductor, same deal, 240 squared divided by, now we're going to go into my XL. Don't be using the straight inductance that we have, but use that XL of 15.833. Ooh, I think I went too far there. I only have 2 decimals yet. And that equals a value of 3,637, so 3637, and if I take a look, it's 0.97, so that's going to go and round up to 0.98 to 0.99. We're just going to call this 3638 bars that we are going to have. I am going to identify these as vars L, because I've got an equivalent number, due to the fact I've got the same XC, and it's the exact same calculation that we would have, 240 squared over 15.833. I'm going to have the exact same number of bars C here, 3638 bars C over here. Lovely. So if I were to go and add this all up and try and create a triangle, it wouldn't work. We know that we'd have 2880 watts out. I'm going to go and have my vars L, and then I'm going to have an exactly equal amount of vars C back down. And I see that I would end up at this point over here. These two would have just canceled each other out, leaving us only with this 2880 VA, or 2880 watts. Because we're at resonance, our watts now become our VA. They're all that I see inside of the system. Yes, these vars exist, but they're just playing catch with each other with current at this end. So my total VA seen by the circuit, VA equals 2880. You can write it as VA or you can write it as watts in this case, because it is only watts that's going to be inside of there. Okay, so that is going to go and be my power. Now what I can do is I can figure out my values of current. Well, if this is my VA, I can divide that by my voltage, and it's going to tell me my current. So we're going to do that. We're going to go and take, well, actually, before we do that, let's do these ones over here, because I've got these vars over here, and if I divide them by the value of voltage, 240, then I should get my current out of that. So we might as well do that since that number's already in our calculator. Here's my 3637. I'm going to divide it by 240, right? It's a form of power, so power is volts times amps. So if I divide out the volts, I end up with the amps. I'm going to have a capacitive amps of 15.15 amps that I'm going to go and have. Do that right over here. 15.15 amps over here. That's going to be capacitive. And because they're the exact same value that I have over here, same vars C and vars L, that would mean that for my inductor, it's also going to have to be 15.15 amps, but now it's going to be inductive. And these two currents are going to be passed back and forth between the two components. Well, that leaves our very last component for this to be my line current that I'm going to go and have over here. And if we take a look at this, we see that the only thing that my source is feeding, because these two are passing their current back and forth, the only thing that my source is going to go and have is this 2880 watts. So if I go and take my 2880 watts, 2880, divided by 240 volts, I see that I'm going to go and have a grand total of 12 amps. 12 amps that we are going to go and have coming from the supply going up and through here. We're going to go and have two main current paths inside of here, and I'm just going to erase a bunch of values. We found all the values, we've calculated them, different methodology than what the book uses. Neither their methodology nor my methodology is more correct. It's just different ways of going about and dealing with these ones. But if we take a look at the currents, we're going to see something really, really cool over here. I'm just going to erase a whole pile of extra numbers that we don't need to see here anymore at this point because they kind of just blur what's actually happening. We'll leave that current up there. We'll leave this current up here. We'll leave this over here. So Kirchhoff's law of current states that the sum of all currents that enters a node has to be the same as all currents which are going to be leaving a node. And we define that since we have got a resonant circuit, we've got an XL that's equal to an XC, therefore they're going to go and have the same current. So if I take a look at them, they're going to be same current in opposite directions, which would mean when one is rising, the other one would be going out of the node over here. And when the AC alternates, the other one is going to be going into the node and the other one's going back out of the node over here. Which means that if I've got 15.15 amps entering and 15.15 leaving, to satisfy Kirchhoff's law of current, there must be therefore 0 amps that are going to be flowing inside of this section of my conductors over here. It's pretty trippy. If I take a look at this one over here as well, I see that I'm going to go and have 12 amps that's entering. I'm going to have 12 amps going through the load. Once again, Kirchhoff's law of current states that if all the current that enters leaves here, then therefore this thing must be 0 amps as well. We see it reinforced over here on this supply end. So during operation, there is going to go and be 0 amps. If I get the circuit to true full resonance, I'm going to have 12 amps that's going to be taken by my supply and are taken by my resistive load from the supply. It's just going to be circulating inside of here as AC goes back and forth. But if I take a look at these ones here, I've got a higher value of current. If I were to just stick my ammeter around here, I would measure 15.15, and that would be fine. I'd measure the same over here, but if I were to measure this, I would get 0 amps. The only time that I do get current that is going to go and flow through this set of conductors that I have over here is going to go and be on my initial powering up of that circuit. Because initially, what's going to have happened is my capacitor has got a discharge path through that inductor, which means it's going to go and equalize its charge, right? Nature tends to want to go and balance. So the instant that I close in on this circuit over here, again, I put a switch in there. When I close that switch, what I'm going to get is I'm going to get current that's immediately going to start, the 12 amps that's going to go through here. And then I'm going to go and get current that is also going to get delivered out to this cap over here. And it's going to go and build up on that cap. It's going to drive electrons away from the other side like that. But it's only going to continue to build until it fills that plate, till the electrostatic lines of force are giving us all that pressure, and the electrons, we got the maximum number on that plate. Once we fill this thing to its maximum, based upon what that is going to go and be, right? Q, our coulombs that we're going to have, then this current shuts off. This one continues to go, and at that point, the electrons that we've stored on here start to do their swish, swish, back and forth inductor to capacitor at that point. All around, it's a fantastic, fantastic thing, because we see that we can take a load that has got some inductance, some properties like that, but we can go and just only once take that current in, and then after that, we just pass it back and forth. We just get to recycle that current, reuse it, and we're not continuously taking it from the source. Once again, we've got tons of these types of loads, right? Ballast, transformer, motors are 3 big ones. And as a result, we got a lot of these inductive VARs, so we're going to see a lot of using capacitors so that we don't have to continuously supply the inductive VARs. All right. That's it for the resonant one. We've got one more video. Oh, man, this is a long learning task, which is going to go and deal with practical AC circuits, where we're going to go and have series parallel RLC circuits.